Good evening. So, in this uh, lecture, we will discuss the next properties of tree. Okay, these are some of the equivalent conditions. Okay, so let G be a graph with n vertices. Then the following are equivalent. So here there are five conditions are given. So we should assume G is tree. You need to prove what? Okay, any two distinct vertices of G are joined by a unique path. Second one, third one, G is minimally connected. Fourth one, G is connected and has n minus one edges. And last one, G is acyclic and has n minus one edges. So actually, we need to prove they are equivalent. Means we need to assume one, and then you should prove two. Again, you should assume two. You need to prove three. Similarly, you should assume three. You need to prove four. And you should assume 4, you need to prove 5, and then assume 5, and then you should prove what 1. So here okay, maybe some other things already we discussed. Okay. So let G be a graph with n vertices, then the following are equivalent. Okay, so first you should assume G is tree. You need to prove what? Any two distinct vertices of G are joined by a unique path. Okay. So what you need to assume here, G is a tree. You need to prove, or you need to prove any two distinct vertices of G are joined by a unique path. Actually, this is property number one. So you need to assume G is tree. So in a tree, any two vertices are joined by a unique path. Actually, this property we discussed in the lecture number 7. I think so. Lecture number 7. I don't know exactly. Yes, I think lecture number 7. So you can verify it. Okay, I don't want to repeat again. Next, assumes 2. So 2 is what? Uh, any two distinct vertices of G are joined by a unique path. Okay, you need to prove G is what? Minimally connected. So okay, so I think the last lecture. Okay, we proved mm, G is okay. So what is the assumption here? Assumption is okay. I should write like this. Okay, so here I should write the proof like this. Okay, so maybe I will take into a snapshot. Maybe I'll put it more. So assume two here. Okay, what is two? So this is two. Okay, you need to assume two. You need to um, I need two distinct vertices of G are joined by a unique path. So you need to prove G is what? Minimally connected. Okay, there is no need to write these things. Yeah. Okay. I should start the proof. So first assume, assume any two distinct vertices of G are joined by a unique path. That is the assumption. Next, to prove G is minimally connected. Suppose, suppose, okay, suppose G is not minimally connected. You should start like this and get some contradiction. Suppose G is not minimally connected, then there is an edge. E is equal to UV. Okay, E is equal to, I think in the last lecture also we discussed, E equal to UV, if such that if I remove E from G, okay, you will get this graph. So this is G minus E. Is still it is connected. Okay, as G minus E is connected, there is a UV path P. This is the UV path P in G minus E. So in G, the path, this is the path P. Okay, path P together with what? The edge E will form a cycle. So which is the contradiction to the assumption, okay, which is the contradiction to the fact, okay, not is okay, will form a cycle, okay, so okay, so um, so in G the path P together with the edge E will form a cycle. Okay, now this is a contradiction to what? So what is the assumption? Any two vertices of G are joined by a unique path. So this is a contradiction to the assumption. Why there is a contradiction to the assumption? So yeah, you should write which is a contradiction to the assumption what? Which is a contradiction to the assumption any two distinct vertices of G are joined by a unique path, because you will get a two different path. One is from U to V, you have, this is one path, this is what? Another path. Okay. So why you are getting this contradiction? Because you are assuming what? G is not minimally connected. So G is what? Minimally connected. Next, I think 2 implies 3 is over. Next, 3 implies 4. 3 is G is minimally connected. You should assume this, and then you need to prove G is connected and has n minus 1 edges. Okay. So first, the last lecture, I think lecture number the previous lecture, uh, we proved okay, G is minimally connected. G is minimally connected if and only if what? G is a tree. So what is the assumption here? G is minimally connected, and hence automatically connectedness will come. Okay, but you need to prove what? It has n minus 1 edges. Okay, so minimally connected implies connected. Okay, that is fine. Now minimally connected implies G is also tree. Okay, G is a tree. That is already in the last lecture we proved. G is a tree. Only thing I need to prove what? It has n minus 1 edges. For this part already we proved. That is a tree with the n vertices has n minus 1 edge. This is the proof. So maybe I think seventh lecture we discuss this portion. We can write this. Okay, again I'll tell you what you need to do here. Assume 3, that is G is minimally connected. You need to prove what? G is connected and has n minus 1 edges. So minimally connected implies connected. Over. So minimally connected implies tree. Okay, so now G is a tree with n vertices. Only thing I need to prove, G has n minus 1 edges. So for this, uh, I think the seventh lecture, uh, I proved a tree with n vertices has n minus 1 edges. So you should give the proof here. Okay, so that's why already we discussed this one. That's why I'll skip. Next, I should assume 4. So what is 4? G is connected and has n minus 1 edges. G is connected and has n minus 1 edges. So you need to prove fifth one. Assume 4, you need to prove 5. So what is phi? G is acyclic and has no and has n minus one edges. Okay. So I think n minus one edges is also in the assumption. I don't bother about n minus one edges. Only thing I need to prove what G is acyclic. Okay. Suppose G contains at least one cycle. I start the proof like this. T contains at least one cycle. So let C1 be a cycle. Okay, maybe I will take a snapshot and then I will. So I need to prove G is acyclic. Okay, suppose T contains at least one cycle. Let C1 be a cycle in T. Okay, now uh, we are constructing a new graph T1. Okay, just we are removing an edge E1 from C1. Okay, so this is your T. From T, I am getting what? Okay, T1. Okay, T1. The vertices is what? Same. There is no change in the vertices, but from E, E is a set of all edges in T. How many edges it has? N minus one edges. So now T1, I removed one edge. Okay, or E1. Okay, this new graph contain all the vertices of T and also all the edges of T except the edge what E1. Okay. Since E1 is an edge of the cycle, okay, comma, T1 remains still it is connected. T1 is what? Connected graph with the n vertices. Okay. Suppose T1 contains a cycle C2. Let E2 be an edge, okay, of C2. Okay. Then T2 is equal to, okay, the vertices again what? Same. From the edge, I am removing, already I removed E1, now I am removing what? E2. Okay. And we know that T2 is also what? Connected because we are removing an edge in the cycle. So that's why the resulting graph is still it is connected graph. T2 is connected, but how many vertices? N vertices. Okay. Suppose if T2 contains a cycle, okay, so then we repeat the process, okay. Okay. Since T contains a finite number of cycles, okay, this T contains a finite number of cycles, we obtain a connected graph. If we go like this, uh, okay, so maybe T2, T3, T4, Tk. Tk is equal to the same vertices. There is no change in the vertices, only edges. The Tk, I removed what? Ek edges. Okay, wow. E1, E2, Ek. Okay. Suppose Tk has which has no cycle. So Tk has no cycle. So and we know that it is Tk is what? Connected. Tk is what? Connected. And suppose it has no cycle. So connected plus no cycle implies it's a tree. Which one is a tree? Tk is what? Tree. Okay. How many vertices? There is no change in the vertices. So n vertices. So a tree with the n vertices has how many edges? N minus one edges. Which one? Tk. Okay. Tk has n minus one edge means T T should have what? How many edges? And we know that in the assumption n minus one edges okay, uh, we assumed, but we removed how many edges now? K edges we removed E1 to Ek. So if Tk itself has n minus one edge means okay, T should have okay, T should have n minus one plus K edges. Which one? T. Okay, but the n minus 1 plus k is greater than what? N minus 1. Because our assumption is what? T has n minus 1 edges. Now you are telling what t has how many edges? T minus 1 plus k is greater than what? N minus 1. So this is a contradiction to the assumption. Okay, so why we are getting this contradiction? We assumed what? T contains what? At least one cycle. So and hence T has no cycle. So that is a proof. And fifth, I should assume 5 and then prove first one. So what is 5? G is acyclic and has n minus 1 edges. So you need to prove G is what? A tree. Okay. So just G is acyclic and has n minus 1 edges. This is assumption. You need to prove G is tree. So to prove G is tree, you need to prove two things. One is connectedness and has what? No cycle. So okay, the assumption itself it is acyclic. So and hence no cycle. It is automatically is true. Only thing I need to prove what? Connected. Suppose the graph is assumed. Suppose the graph is what? Disconnected. Disconnected. So and hence it has what? K components. I think the last lecture we discussed. Okay, this part. Okay, if G has K connected components. For example, this is the first component, this is the second component, this is the kth component. It has n1 vertices, first component has n1 vertices, second component has n2 vertices, third component has nk vertices. So each one of them are connected and has no cycle because G is what? Acyclic, and hence each component is what? Okay, kind of acyclic, or each component has no cycle. So connected plus no cycle implies it is what? Each one is what? Tree. Each one is tree. So tree with the n1 vertices has how many edges? N1 minus 1 edges. Similarly, tree with n2 vertices has n2 minus 1 edges plus dot dot dot. The tree with nk vertices has nk minus 1 edges. So this is the total number of edges in what? G or T, whatever it may be. So n1 plus n2 plus nk is what? N. How many ones? K. So n minus k edges in where? G or T. But you are assuming what? G has n minus 1 edges. So this is equal to n minus 1. This implies k equal to what? 1. K equal to 1. So that k equal to 1 means we have only one component. So and hence G is what? Connected. So connected, already we know that it is what? No cycle, and hence G is a tree. So that's a proof. Okay. So look at this one. Just to quickly, I want to tell the last equivalent condition. Okay. Yes. So here, so this is the last equivalent conditions in trees. Let G be a graph with the n vertices. Let T be a graph with n vertices. Then the following conditions are equivalent. Okay, the first one is what? T is a tree. Second one is every two vertices of T are joined by unique path. Third one is T is connected graph and has n minus one edges. Fourth one is what? T has no cycle and has n minus one edges. Okay, so these results. Look at this one. Okay, I think this is in our PPT. So P comma Q graph means P vertices and Q edges. Then the following are equivalent. G is a tree. Okay, here T is a tree. So here every 2 points of G are joined by unique path. The same condition. Third one is what? G is connected. Here T is connected and T has how many edges? N minus 1. Here P equal to Q plus 1. Or you can write what? This is Q is equal to what? P minus 1. So Q already I told that Q is what? Number of edges. P is what? Number of vertices. So number of edges is what? P minus 1. Here the number of edges is what? N minus 1. So N is the number of vertices here. And then similarly last one. Acyclic. Acyclic means no cycle and it has N minus 1 edges. Okay, from this also Q is equal to what? P minus 1. So these four conditions are same as these four conditions. Okay. Now, one implies two already we proved. Okay, T is a tree. If you assume, you should assume T is a tree. You need to prove what? Every two vertices of T are joined by a unique path. So that is already we discussed. Next, you should assume two. Okay, you should prove three. So every two or any two vertices of T are joined by a unique path. You need to prove what? T is connected and has n minus 1 edges. Okay. So any two vertices are joined by a unique path means from the assumption itself, T is what? Connected. So connectedness automatically from 2 implies 3, connectedness automatically comes. The only thing we need to prove T has how many edges? N minus 1 edges. Okay. So from the assumption, any two vertices are joined by unique path implies T connected and has what? No cycle because between any two vertices there is a unique path. So and hence there is no cycle. Okay. So from the assumption we will get a connectedness also and also from the assumption we will get what? No cycle also. So connected plus no cycle implies what? T is what? Tree. So we proved T is a tree. Still, I need to prove what? It has n minus 1 edges. So T is a tree. T is a tree with how many vertices? N vertices. N vertices. So if it is a tree with n vertices, is what? How many edges? We proved already. N minus 1 edges. So depending upon the mark, okay, they are giving more marks means you need to give the proof for this part. You should assume T is a tree with n vertices. You need to prove what? It has n minus 1 edges. You need to prove n minus 1 edges means you should give which proof. Just I'll tell you the proof. Okay. Yes. Theorem number 9. So tree with n vertices has n minus 1 edges. You should give the proof up to this. Okay. Next, I think we discussed 2 implies 3. Next, 3 implies 4. T is connected graph and has n minus 1 edges. We need to prove what? T has no cycle. T has what? No cycle. 3 implies 4. We are going to prove. Okay, 3 implies 4. I'll go to the PPT here. 3 implies 4. Yeah. Again, I'll tell what is 3. 3 is what? T is connected graph and T has what? N minus 1 edges. So we need to prove T has no cycle, uh, no cycle. Okay. T has no cycle and has N minus 1 edges. Okay. So, yes, n minus 1 edges is already in the assumption 3. So, we will get easily n minus 1 edges. Only thing I need to prove what? No cycle. So, this one already we discussed. Okay. Suppose, suppose T contains at least one cycle. Okay. So, this part we discussed in the previous theorem also. We are removing edge. Okay. E1 from the cycle C1 will get T1, okay, and then we'll get T2 and then we'll get TK. So TK is what? TK is a connected graph and it has no cycle. So and hence TK is what? Tree with n vertices. So and hence TK is also has n minus 1 edges. But the original graph T itself what? Has n minus 1 edges. So that is a contradiction to the assumption. So why we are getting this contradiction? Because T contains what? We assume it has at least one cycle, and hence T has what? No cycle. So that is the end of the proof for 3 implies 4. Next, 4 implies 1. 4 implies 1 is what is 4? 4 is T has no cycle and has n minus 1 edges. You need to prove T is a tree. So no cycle, T is a tree I need to prove. So to prove T is a tree, I need to prove two things. One is connectedness, another one is what? No cycle. But in 4, we assumed no cycle. Only thing I need to prove what? Connectedness. So this part is also already discussed. Okay. Suppose to prove T is connected, I need to prove T is what? Connected graph. Suppose this T is not connected. So take T1, T2, Tk. I put a box like this. Okay, it has k components. Okay, you can I think yes like this. So this is the first component T1. This is totally it is T. This is T1. This is T2. This is Tk. So totally k components. So each of them is connected and each of them has what? No cycle. Okay, because uh, in the assumption, what is the assumption? 4. 4T has no cycle and each component has what? No cycle. Okay. So here, yes, suppose T1, T2, Tk are what? Components of T. Since T has no cycle, that is the assumption. Okay. We from this uh, from this T1, T2, Tk are connected graph and has no cycle. So, and hence connected and no cycle means what? Each of them are what? Tree. So T1, T2, Tk are all tree. So it is a tree means how many vertices T1 has? N1 vertices. So then how many edges T1 has? N1 minus 1. Similarly, T2 has N2 vertices and hence T2 has N2 minus 1 edges. Finally, Tk has Nk vertices and hence it has Nk minus 1 edges. The total number of edges in T is what? The total number of edges in what? T1, T2 up to Tk. If you add everything, you will get total number of edges in where? In T. So, and hence uh, we know that N1 plus N2 plus Nk is what? N minus k. So T has how many edges? N minus k edges. But originally you assumed T has n minus 1 edges. So n minus 1 equal to n minus k. From this k equal to 1, and hence k equal to 1 means T has only one component. Only one component means it is a connector. But yes, we proved T is what? Connected graph. And also we know that T has what? No cycle and hence T is a tree. So all the properties are over. Now next class I am going to start uh, a planar graph. Okay, planar graph. This is the important section, planar graph. Maybe I don't know how, maybe uh, one or two classes we need for planar graph, and then I'll go to Prince, Kruskal, and Dijkstra. Okay, I'll stop here.